In today's lesson, we're going to be looking at the reactivity series. This is Unit 2, Unit 2D of the specification. We won't go through all of it. Okay, so 2.15 and 2.21, you've got to understand how these metals can be arranged in order of their reactivity. Now you can react them with water or react them with hydrochloric acid. Now, with your water, it's normally your group 1 metals which you react with water, and you can see which ones are more vigorous, and you know that lithium is less vigorous than sodium and is less vigorous than potassium. With potassium, you get your lilac flame, and then with sodium, it forms a ball, and with lithium, it just kind of fizzes, doesn't form a ball, and it kind of shoots out as well. Sodium does. So you can see that the reactivity increases as you go down the group here. With dilute hydrochloric acid or sulfuric acid, however, it's too reactive to use on group 1 metals, but we can use it on these metals down here, magnesium, zinc, and iron. Now you can just look at the bubbles and just see which one. You can see which one releases most bubbles or which one effervesces more. You can see that it gets less reactive as you go down here. Okay, so there's two ways that you can see which ones are most reactive, and you can either use a test tube way, count the bubbles, or you can use the calorimetry way. So you can use a calorimeter, which is just a fancy word for this polystyrene cup here, which we're going to measure the temperature in. And we're going to measure the temperature of this reaction, how much heat is being released from here, from this cup here. Some heat will get out, and we're going to have some heat lost some heat escaping. But polystyrene is a pretty good insulator, but we'll mostly get the heat escaping out of here, so not the most accurate results, but they're good enough for this experiment. So when we're doing this experiment, we're going to measure the temperature, and whichever one has the max temperature increase, that's the one which gives the most vigorous reaction. Here we can see it's magnesium, then zinc, then iron, then copper. Now in this experiment we need to keep the variables the same, and some of the variables we keep the same. We try to keep initial temperature the same, but I mean there's some variation, but it doesn't really matter. There's one variation there, but this is what matters the most here, the mass. Not really the mass, but the moles. We need to keep the number of moles the same, so the amount. We need to keep the number of particles the same, and when we're talking about number of particles, we always refer to the number of particles using moles. So we've used the same number of moles of each of these substances, and as you can see, each of these values is actually the same. There's actually the same numbers as the MR of each of these atoms. So magnesium's MR is actually 24. That's its mass number. So we've actually got, so if we had 24 grams, we would have 1 mole, but we actually have 100 times smaller than that, so we actually have 100th of a mole, and it's the same with each of these. We actually have 100th of a mole. It's just that the atoms just weigh differently, but we have the same number of atoms, which is 6.02 times 10 to the power 23 divided by 100. That's how many atoms we have of each of them. Okay, next part of the spec, I'm going to give you about 3 minutes just to look at the definitions for these words. You need to know them, so make sure you can remember them. In terms of gain or loss of oxygen, and in terms of electrons and oxygen, sorry. Okay, these are the definitions that you should have got. Now we're going to look at these definitions in comparison to this reaction here. So if we look at magnesium here, magnesium is actually gaining oxygen, so it's plus oxygen, but therefore it's being oxidized. It was copper oxide, it's losing oxygen, therefore it's being reduced. So that's in terms of oxygen. What about in terms of electrons? So if we look at magnesium, that's got a full outer shell. It's neutral, so I'm going to put 0 there. It's neutral. The magnesium on this side, however, now it's become an ion. It's actually lost 2 electrons, so it's become 2 plus. So it's lost 2 electrons. So we're going to we'll put that on the side here, lost. So minus 2 electrons. It's actually there, so it's lost. So it's lost 2 electrons, therefore it's being oxidized. It's lost electrons, and copper oxide here, we've got it's 2 plus here. Then it becomes by itself, it becomes 0, so it actually gains electrons. So I'm going to put plus 2 electrons here. Now to remember this, a lot of scientists use this oil rig. It's an easy way to remember oxidation and reduction in terms of electrons. Now this reaction is a metal plus metal oxide. This is a displacement reaction now, or a competition reaction, whatever you like to call it, but this we'll see a bit later on as well. So magnesium here is actually formed an ion. Magnesium here is formed an ion, and oxygen stays an ion. Now we can write half equations to this reaction here, just to show us what's actually happening with the electrons. And so if we, this sentence here is going to help us. So we have magnesium here, it was 0, and it actually reacted to form an ion, magnesium 2 plus, but it also lost 2 electrons. So because we lost 2 electrons, I'm going to put the 2 electrons on the other side. It split to form them. Okay, so copper, now we can do the same with copper. Copper started off as an ion. I'm just going to put an ion there, then it became, I'm just going to leave some space there, and I did that with magnesium just in case we are putting electrons there, but for magnesium we didn't. So copper, that actually became an atom. So we put the electrons on this side. So copper, we added 2 electrons there. Okay, and those are your half equations, which shows what atoms gaining electrons and what atoms losing electrons. Now note here, the oxygen actually stays as 2 minus, so it's what we call a spectator ion. It just it doesn't take part in the actual reaction. No electrons are being moved. Take just under 3 minutes to answer these questions. Okay, so our first question is state why this reaction is described as a redox. Now redox is when reduction and oxidation is happening at the same time. So I'm just going to put here oil rig, just because we know that it's in terms of electrons, because there's no oxygen atoms here, so we must talk about this in terms of electrons. So if we look here at what's happening between electron transfer, so we've got magnesium to magnesium 2 plus, magnesium is losing 2 electrons, therefore it's becoming oxidized. This is this first part here. It's becoming oxidized if you think about oil rig. Your silver, on the other hand, that is gaining 2 electrons. So each silver atom is gaining 1 electron, but there's 2 atoms, so they're gaining 2, and that is reduction. Okay, so this is a redox reaction because oxidation and reduction is happening at the same time. Now here it says explained in terms of electrons, so we can use that word in our answer. Which species is behaving like an oxidizing agent in this reaction? So an oxidizing agent that oxidizes something else. So if we're looking here again, it oxidizes something else. So it causes something else to lose electrons. Therefore, it itself must gain electrons. So which one of these species here gained electrons? Okay, so we have the silver. So the silver is the oxidizing agent because it gained electrons or took electrons from magnesium. We can also order metals in their reactivity, in their order of reactivity, by reacting them with metal oxides. Now, we talked about that earlier, and I said we'll come back to it. And lo and behold, we have. So magnesium, well, magnesium here is reacting with copper oxide, and it's displacing copper. It's displacing the copper from the copper oxide. Therefore, it is more reactive. So if we had a reactivity series, magnesium would be higher than copper because it displaces it from its compound. Copper is therefore going to get kicked out, and it's going to be by itself, which it is, and you'll actually in this reaction see some brownish red copper here. Okay, so that's for metal and metal oxides. Looking at metals in aqueous solutions, I've got an example here, and we're going to look at what's happening here. So zinc is, as we can see, is displacing copper. Copper is then going to be by itself. So zinc is displacing because it's more reactive. Okay, and then that means zinc is higher than copper in our reactivity series. So doesn't look nice. Okay, if you wanted to find out whether magnesium is more reactive than zinc, like where does magnesium come, because we know magnesium is higher than copper, we have to do magnesium sulfate or zinc sulfate reacted with the other. So let's do magnesium sulfate plus zinc, and if zinc kicks out magnesium, if it displaces magnesium, then it's more reactive. If it doesn't, then it's less reactive. And in fact, it doesn't, therefore magnesium is higher. Now we can also show what's happening with the electrons by writing out half equations. So I'll just put this out so we've got space. And we do that by writing out the charges above each of the metals. So zinc is 0 here, so it's neutral in terms of the charge. Copper is 2+ here. That's because I know copper sulfate molecules are 2-. That's your golden 5. Zinc here is going to be 2+ as well. Copper here is 0. So if we write these out, let's do zinc first. Just to show what's happening with the electrons. So zinc, going to leave some space. Going to leave some space. So just in case we want to add electrons there on the other side. So zinc reacts to form zinc atoms react to form zinc ions, and they lose 2 electrons, so the electrons go on the other side. Copper, on the other hand, copper ions, again I'm going to leave some space, they react to form copper atoms, and your copper ions gain electrons to form your copper atoms. This is what happens, and this is our ionic equation, both ionic equations. Now both of your electrons, they need to be the same. Okay, if they weren't, then you just need to multiply one of the equations, kind of like simultaneous equations in maths. Your sulfate ions, they don't change charge, they stay as 2-, so they're what we call spectator ions. Spectator ions. Again, we can draw ionic equations to see what is happening with the electrons in our reaction here, in our displacement reaction here with ionic salts, metals and their salts. So copper is displacing your silver from its nitrate. If we just write the charges here, copper is 0, Ag is minus, NO3, Ag is plus, sorry, NO3 is minus. Copper here is 2+, NO3 is minus, we've got 2 of them. And then Ag here is 0. So if we start off with the copper, what's happening with the copper? Let's leave some space there. We could also put solid here, put the state symbols in to show that solid copper, that doesn't look good. So we have solid copper, I'll leave a bit more space. What is happening? It's changing into an ion. So a copper atom is turning into an ion, plus 2+. Therefore, we're going to have 2 electrons on this side. Okay, that's our ionic equation for that. Our Ag, so our silver. Our silver, we've actually got 2 silver atoms actually. So 2 silver atoms, they are forming 2, what's that, silver. So we have 2 silver ions, plus forming two silver atoms. Let's put solid here. Aqueous. Aqueous. So each silver atom is combining with an electron, and we're forming our solid silver, and that's our crystals. There's our silver crystals that's forming on the outside of this beaker here, which look very pretty. So metals also form crystals, regular repeating patterns of atoms. Now, in terms of electrons, we're looking at oxidation and reduction. So if we're looking at which one's being oxidized, if we remember the oil rig, so oil oxidation is loss. So the thing that's losing electrons is the copper. Copper atoms is losing electrons to form an ion, to form ions. Okay, so this is your copper atom, and reduction is going to be your silver. It's going to be the opposite way around. Then your oxidizing agent and reducing agent, they're always the opposite. So if copper's being oxidized, then it's going to be the reducing agent. And if silver's being reduced, then it's going to be the oxidizing agent. It's causing the other one to be oxidized. Okay, I'm going to give you 3 minutes to answer these questions. Okay, so you should have got these. I'm going to give you 2 minutes to answer these questions. Okay, so for this, sometimes it does help to write out the equation or what's happening here. So we have two metals. We have magnesium powder. So we have a silver magnesium powder added to copper sulfate. That's going to react. Your magnesium is going to displace your copper, so you're going to get magnesium sulfate plus your copper by itself. So your first observation that you'll see the copper, you'll see the reddish brown copper. The second one is, you know that copper sulfate is blue. That's going to turn to colorless because magnesium sulfate is colorless. And most of the sulfates that you come across in GCSE are going to be colorless, except for your copper sulfate, which is blue, characteristically blue. Okay, so you need to know how rusting happens and some of the ways that we can prevent it, because it's iron's a very important metal used in transport. So barrier methods, we can use paint, oil and grease, although there's some disadvantages here that if the metal scratches, then it's left unprotected, so that can be quite bad. Okay, so we've just done barrier. I'm going to go to sacrificial protection now. I'm just going to jump there and you'll see why after, because sacrificial protection is when you use anodes like this, like on this ship. And this is like you use a more reactive metal. This is like zinc, which is more reactive. And the more reactive metal prefers to lose its electrons. Therefore, in this reaction, zinc prefers to lose its 2 electrons, and it gives them to any ion that reacts. So any ion that does react, it gets electrons from zinc to go back to iron. So iron actually doesn't end up forming ions, so therefore can't rust. So iron doesn't end up rusting in that sense, and that is sacrificial protection. Now, galvanizing is a mixture of a barrier method and a sacrificial protection, because you layer something. Normally, it's something small, because large ships like this you can't galvanize. You can't galvanize a large ship like that. It's just too big. So normally, like small watering cans or something like that, you'll galvanize, or something like that, or jewelry or things like that. So galvanizing is a mixture between a barrier method and a sacrificial protection. So once your zinc layer is exposed, or it doesn't it still doesn't rust, because then it starts to form a sacrificial protection if there is some part that is exposed. Okay, spend 3 minutes on answering this. First one is galvanizing, and these are answers for your second one.